Hi, and welcome to part 1 of this KD video series. In this video I will go over what the dissociation constant KD is, and how it is derived. But before we get into that, I want to take you through some of the fundamental details that underlie KD. So in a biochemical reaction, equilibrium is the state in which the proteins, ligands, and protein-ligand complexes are at a point where there is no observable change in the properties of the system. A common misconception is that there is no longer protein-ligand complex being formed and dissociated. However, this is not the case. Once equilibrium has been reached, it means that there is the same number of complexes forming and dissociating at any given time. One way to think of this is imagining a person running in place on a treadmill. The person is traveling forward at say 10 miles per hour, and the treadmill belt is traveling at the same speed but in the opposite direction. Both the treadmill and the person are constantly in motion, but because they are traveling in different directions, there is no net movement. Before we look at defining the dissociation constant KD, we must first define the protein-ligand interaction equilibrium. This equilibrium represents a dynamic relationship between the unbound protein, its respective ligand, and the protein-ligand complex in a given system. It should be noted that the ligand could also be another protein or something else, such as a small molecule. Protein-ligand binding can be represented by the equation on this slide. Here, P represents a protein, L is a ligand that combines the protein, and PL is the protein-ligand complex. As this is an equilibrium, not all the ligands are bound to the protein. Some of them are bound and some of them are free in the system. Here is the same equation again, but now we are going to describe the two directions that govern the equilibrium of the reaction. K(on) is a rate constant, the value of which stays the same for a given pair of proteins and ligands. It describes the rate at which the forward reaction is taking place, so that protein-ligand complex is formed. This rate is dependent on the concentration of the proteins and ligands, and is measured in per mole per second. On the other hand, the K(off) describes the rate of the backwards reaction. It depicts the rate at which the complex dissociates into separate proteins and ligand. This rate is independent of the concentrations of the free protein and ligands in the system, and it is measured in per second. So what is KD? KD is the dissociation constant, and is the concentration of ligand where half the ligand binding sites on the protein are occupied in the system at equilibrium. It is calculated by dividing the K(off) value by the K(on) value. It is also equal to the product of the concentrations of the ligand and protein, divided by the concentration of the protein-ligand complex once equilibrium is reached. The units for KD are measured in molar. This might seem confusing at first, but if we look at the equation above as a set of units, then it becomes clear. The smaller the KD, the more affinity two proteins have for each other. So now let's take a look at Ka, the association constant. Having now described the forward and backward rate constants, and KD, it is time to look at the association constant Ka. Ka is the opposite of KD, and is calculated by dividing the K(on) by the K(off). Because of this equation, its units are measured as per molar, which is why scientists prefer to work with KD since molar is easier to work with. KD is an equilibrium description, and is not representative of the concentrations of proteins and ligands in any given system. This is something to always bear in mind. In the following 3 examples I'm about to go through, the KD for the system will always remain at 3. So in the first example, there are 8 proteins and 3 ligands. They are in the system with the KD of 3. That means there will always be 6 free proteins, 1 free ligand, and 2 protein-ligand complexes at any moment in time. If we look at a system where there are 6 ligands and 6 proteins, to meet a KD of 3, there will always have to be 3 proteins, 3 ligands, and 3 protein-ligand complexes at any given time. The final example is a reverse of the first, so that there are 3 proteins and 8 ligands this time. Here to meet the KD, there will always have to be 1 free protein, 6 free ligands, and 2 protein-ligand complexes at any given time. And that's it. A second video that will cover how to generate a binding curve and derive the KD from the graph is also available. The link is in the description below. For more educational content regarding the dissociation constant, please visit our website. If you've enjoyed this video, please like and subscribe for more content. Thanks again and have a nice day.